All right, so we're going to talk about chain rules. So remember, for a single variable function, y equals f of x, and if we had x is some function of t, some other variable, then if we wanted dy dt, the chain rule tells us that is dy dx, dx times dx dt. And for multivariable functions, it's going to follow a similar pattern, but just like we have several second partial derivatives, we have several chain rules, depending on how our variables depend on other variables. So we're going to talk about a couple of cases. So for multivariable functions, we're going to say this is case 1. And we're just going to do the two variable functions. What we talked about will extends just like we'd expect to functions with more variables. So case 1, we're going to have z equals f of xy, and x is some function of t, and y is some other function of t. So z is indirectly a function of t. And we're assuming that z, g, and h are differentiable. So we're working with nice functions. So dz dt is the partial of z with respect to x times dx dt, plus we have to add in the part where z is changing with respect to y. So we have partial of z with respect to y times dy dt. And notice I use the normal d's for dx dt and dy dt because those are just single variable functions, and we use a normal d for the partial or the derivative of z with respect to t because that's if z is implicitly a function of just t. So that's how we're going to take the derivative if x and y are some functions of another variable. Well, we can also have x and y functions of more than one variable.
Oh boy.
So that's going to be our case 2. So case 1, x and y are just a function of a single variable. So case 2, we're going to have z equals f of xy, and x is some function of s and t, and y is some function of 8 of s and t. So x and y then are also multivariable functions. So z is indirectly a function of s and t. So z varies with x and y vary with s and t. So what we're going to do is apply case 1 to each. So the partial of z with respect to s is going to be the partial of z with respect to x, and then we get the partial of x with respect to s, plus we have to take into account that z varies with y as well, and then we get the partial of y with respect to s. These are all curvy ones because all of these functions are multivariable functions now. So that would give us the partial of z with respect to s. So applying case 1 to that derivative, and dz dt we'll just use case 1 there. Partial of z with respect to x times the partial of x with respect to t, plus we have the y portion, partial of y with respect to t. And when we take these derivatives, we want to, for each case, we want to express our answers in terms of the independent variables. What did I do? Dent, add an extra en there. Independent variables. So what we're saying is so first thing in the morning this thing runs, my computer runs really slow. So independent variables s and t. So we don't want our answers in terms of x and y. We want our answers in terms of s and t. So a visual to help us remember, if we need help remembering, is a tree diagram. So are we good with the idea here? So we're saying for all of these, this for whether or not we're talking about a tree diagram, z, we call z the dependent variable. X and y are called the intermediate variables. And s and t are the independent variables. So the tree diagram, we start out with our dependent variable here. And I'm going to do just a tree to our different variables. So these are intermediate. And independent. And then we just take derivatives as we go down the branch. So this derivative would be dz dx. And this derivative would be dx ds. So if we wanted dz ds, we'd do dz dx times dx ds. This would be partial of x with respect to t. And then we have to add the derivatives we get down the other branch. So this would be dz dy, dy dt, and dy ds. And we just have a single branch down here, just an s or a t. These last derivatives would be normal derivatives because x or y would just be a function of one or the other variable, not a multivariable function. Yes?
So when we're doing this, when you wrote it all out, it's like dz dx times or the partial dx ds. Can we cancel the dx?
That you can think about it that way, but that's technically not what we're doing.
So you should not.
You should not do that. No.
Okay.
It's a nice way to. That's one benefit of using that differential notation is you can think, oh well, those dx's cancel, and you just get dz ds. But they're really not canceling. It's just a convenient way to think about it. All right, so there's our chain rules. And the same pattern holds if we have a function of more than two variables. You just have to go down your branches. You have additional variables and additional partials that you'll be adding to your derivative. For a three-variable function, we'd have another branch here, and then we'd have the branches from that function as well. And you just keep adding additional branches. All right, so questions? Yes?
So these are not mixed partials where you can just say that like some of like the lower ones are equal?
No. So yeah, not mixed partials. They're products. It'd be nice if it worked out that way. All right, so using the chain rule, not a huge revelation, not really anything different than we've been doing. We're just taking partial derivatives. But there is one tool that comes out of the chain rule that is very, very useful, and that is implicit differentiation. So back in Calc 1, if you remember, you have some function x squared y minus y cubed x equals 5, and you want to find dy dx. So you had to do your derivatives, and you had to use the product rule, and you had to solve for dy dx. There was a lot of algebra involved. Well, with partial derivatives, we can shortcut that process. So let's say we have f of xy equals 0, and assume that y is an implicit function of x. So you have something like yx squared minus y cubed x equals 0. So y is implicitly, you could solve that and get y as a function of x. There's some dependence on x in y, but we can't. It's hard to write it out explicitly. So we're going to say y equals some function of x. So what we have is that f of x equals 0. And we're going to apply case 1 of the chain rule. So we're going to say the partial of f with respect to x times dx plus the partial of f with respect to y times dy dx.
Is that supposed to say dx?
Yes. So we're doing the partial of f with respect to x, partial of x with respect to x, partial of f with respect to y, and then multiplied by dy dx. And that equals 0. Well, what's a dx dx? 1. So we can solve this for dy dx. This is just a 1. Dy dx equals negative, because I subtract this over here, negative partial of f with respect to x divided by the partial of f with respect to y. So this is 1, so I subtracted this and divided by df dy. And usually we're going to say this is minus f sub x over f sub y. So now when we have this implicit function, some function of x and y, x squared y minus y cubed x equals 0, here's dy dx. You can use partial derivatives to do implicit differentiation.
Excellent.
And we're saying here that f sub y is not 0. Much easier. Partial derivatives, pretty easy. Implicit differentiation, if you remember, can be quite algebraically involved. We can extend this if we have our function, if f is a function of more than two variables, x, y, and z, x, y, z, w, etc. And we can find all the partials, all of our derivatives. Similarly, if f of x, y, z equals 0, so x squared y minus y cubed x plus x z cubed minus da 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 e to the z something, or three variable function. And we're going to say z is f of x, y. So z is implicitly a function of x and y. In that case, we can say the partial of z with respect to x is minus the partial of f over the partial z dz dy is minus the partial of y over the partial of z.
Is that dz dy curvy or straight?
This would be curved because z is a function of x and y. So that would be a partial derivative. So we can find the partial derivatives of z with respect to x and y if we have, and this should be a capital F, sorry, because this is small f. So we can find our partials with respect to x and y of a function if we have an implicit a function of three variables, where z is implicitly a function of x and y. All right, questions? This is a really nice shortcut, really nice tool that partial derivatives allow us to do. All right, let's look at a couple of examples. Let's find the partial of w with respect to s and the partial of w with respect to t. And we're going to say w is y cubed minus 3x squared y. X equals e to the s. And y equals e to the t. And we want this at s equals 0 and t equals 1. All right, so partial of w with respect to s is going to be, and this is, I just want to make sure that's a y. Partial of w with respect to x, partial of x with respect to s, plus a partial of w with respect to y, dy ds. That's what our chain rule tells us. I'm just writing out our chain rule results here. Partial of w with respect to t. We're still going to need partial of w with respect to x, and then we need dx dt, plus partial of w with respect to y, dy dt. All right, so let's take our derivatives. Partial of w with respect to x. We get minus 6xy. Partial of w with respect to y. We get 3y squared minus 3x squared. Partial of x with respect to s is e to the s. Partial of x with respect to t is 0. So that's nice. And then the partial of y with respect to t is e to the t. And the partial of y with respect to s is 0. So when I substitute these in, the partial of w with respect to s is minus 6xy e to the s. And in terms of my independent variable, I want to substitute for x and y here. This is minus 6 e to the s, e to the t, e to the s. So we could write that as minus 6 e to the 2s plus t. And then at s equals 0, t equals 1, partial of w with respect to s, substitute those in, and we get minus 6e. So if we weren't evaluating this at a particular point, this would be how we'd want to express our answer. Minus 6 e to the 2s plus t. No intermediate variables in our answer. And now our partial of w with respect to t. Just going to substitute these values in here, and we get 3y squared minus 3x squared e to the t. And with our intermediate variables, we get 3e to the t times e to the 2t minus e to the 2s. And then at our particular point, substitute those in here, and I get the partial of w with respect to t is 3e times e squared minus 1. And we could distribute do other various things, but that's fine. This would be how we'd express our answer if we were not evaluating our partial derivative at a point. All right, questions? All right, let's look at an implicit derivative. So the way you might be asked that question is find the first partials of z. And we have e to the xz plus xy equals 0. So you could go through a process here. This is not an extremely complicated function. You could solve this for z in terms of x and y. It'd be kind of a messy function, but we know that we can differentiate implicitly. So I'm going to say z is implicitly function of x and y. We don't need to find the explicit relationship between z, x, and y. We just take advantage of the implicit relationship. So we know that dz dx is minus the partial of f with respect to x over f sub z, and dz dy is minus f sub y over f sub z. And we're saying f of xy or f of xyz is e to the xz plus xy. So now we just have to take a couple partial derivatives. F sub x z e to the xz plus y, f sub y x f sub z is x e to the xy, or sorry, xz. And we're pretty much done. So dz dx is negative f sub x z e to the xz plus y over f sub z x e to the xz. And the partial of z with respect to y, f sub y, x, got a negative there, x over x e to the xz, which is just negative e to the minus xz. And there we have our partial derivatives. You would get the same result if you solved for z in terms of x and y and then did your implicit differentiation with a lot more work. All right, questions? I want to do one more example where we contrast the chain rule with what we did last time with differentials. I'm going to draw a triangle here. And we're going to say this is theta, and it's a nice isosceles triangle. And we're going to say x is increasing at 1/2 meter per hour. And theta is increasing at pi over 90 radians per hour. We want to find the rate of increase in area. At x equals 6 and theta equals pi over 4. So this is our related rates problem. And we're assuming all these measurements are exact. So this isn't an approximation. So we have a related rates problem. We want dA dt, the rate of increase in the area, the derivative of the area with respect to time. And x and theta are both functions of t. So we need to write a function that gives us the area of this triangle in terms of x and theta. Well, what's our, for a triangle, what's our formula for area? Base times height divided by 2. Well, let's draw in a height here. There's h. So here's our base. So what is this? What is this length? We have a nice right triangle here.
Sine over x, sine of theta over x, sine of 1/2 theta over x.
X equals h. So this is
Cosine theta 1/2 x.
half the base.
X sine of
What is this?
X sine hypotenuse 3069.
B over 2.
Jack, I'm so used to
spitball answers. I got there.
Is that x sine theta over 2?
Yes.
Yeah. What's h?
X cosine.
X cosine theta over 2.
Excellent.
So we have the area equals x squared sine theta over 2 cosine theta over 2.
I mean, yeah, and don't divide by 2 because we actually do want to.
Right. But we don't know theta over 2. But don't we know an identity that has a sine of something times a cosine of something?
Square on both. Theta even.
2 sine.
2 sine theta cosine theta over 2.
Sine 2 theta, just throw a bunch of 2's in there, right? Sine 2 theta, 2 sine theta, cosine theta. So what is this?
1/2.
Sine theta over 2, right? Because we don't have the 2. So this is x squared over 2 sine theta. Phew. That darn trigonometry just keeps coming back.
I don't see that.
What's that?
I didn't see that. Like, what is it? Yeah.
Sine 2 theta, so cosine theta, this angle is twice this angle. Theta is twice theta over 2.
We divide by 2.
Yeah.
Because with this, the identity has a 2 here,
If
so we have half that.
If we needed this identity, would we be provided with this
No,
like,
based on
or are we supposed to know all of these?
Oh yeah,
Well, you're supposed to know all of these, but you would probably be provided with that.
Yeah, we're supposed to know one.
The only one we were told we had to know was sine squared plus cosine squared equals.
Well, that's in pre-calc. That's the only one you needed to know. Yeah, we're not in pre. We're way past pre-calc.
Can't you figure out all the others based off the sine cosine plus sine squared?
Yes. Yeah. All right. So what we're looking for is dA dt. Finally, we need dA dt. Well, the derivative of the area with respect to time, we need the chain rule here because x and theta are functions of t. We get, that's going to be the partial of a with respect to x times dx dt plus the partial of a with respect to theta times d theta dt. Well, what's dA dx?
2x.
X sine theta.
Yeah.
Thank goodness. And what is dx dt?
Can't see
You can't see it.
One half meter per hour.
Why'd you call it
And what is dA d theta? X squared over 2 cosine theta. And d theta dt? Pi over 90. And then, so there's our rate of change of our area with respect to time at any particular value of x. And then we are interested in when x equals 6 and theta equals, what did I say, pi over 4? We get dA dt is 6 sine pi over 4 times 1/2 of that, plus 36 halves cosine pi over 4 times pi over 90. And since we're not in the Calc BC anymore, we're going to do a little more work here. This is, no, this is terrible. You would not want to calculate with this. This is 3 square root 2. 3 square root 2 over 2. Sine pi over 4 is square root of 2 over 2. Plus pi square root 2 over 10. That would be the answer.
We get 9 over 90.
But you don't get to put in a common like that. Put in a common denominator, then all that is one number.
What would that be? 15?
It's like 2.5. It's about like 2.5.
Yes.
Do we need units, or would we get marked off on a quiz or test? We don't have them.
Yeah. Also, I was wondering about units. Is there anything because the theta is radian per hour? Do we have to like convert that all?
No. So remember, radians are unitless. Radians don't have any units.
Okay.
I'm not that worried about units.
If you just write something that's like area measurement that you assume like meters squared.
And this is, again, this is not the area. This is the rate of change in the area per time.
At that time.
At that particular time.
Do we have any more like fun unit adventures where we try to convert them all into the same thing?
Possibly. All right.
One more example.
Questions?
One more example.
One more example?
No.
I only have half a page left.
Only half a page? All right.
That's all you need.
Do your homework on that half a page.
I would've. Last night, realizing I had to rewrite 5 pages of Spanish just because you wanted it.
Just because you can't like mark it on the page.
I made corrections on the page. Like, no,
I didn't say
That
that.
took me like half